Hi guys, today we're going to be going over chemical kinetics and chemical. Oh shit, I'm really zoomed in. I can't even tell without the lines. Okay. All right, so today we're going to be going over chemical kinetics, right? So chemical kinetics is just basically how fast uh something in a reaction becomes something else. So a very simple reaction we could work with is A becoming B. So since A is on the left, means that A is our reactant, which means that A is becoming B, which is in this case the product. Now, A in this reaction is directly proportional to B. How do you write proportional? Something like this, right? So boom, A becomes B. And in order for A to become B, we're transferring it. So that means as A decreases, B begins to increase. That means the amount of A we lose is going to be the amount of B we make. So it means that the rate of what A decreases, B is going to increase. So we could denote this by the the reactant is always going to have a negative value, by the way, because we're losing it. And the product is always going to have a positive value. So the negative change of A in an amount of time, which is delta T, is always going to be equal to the positive amount of the product within an amount of time. So let's have an example where it's better. It's an easier way to visualize it. Okay, so let's try to uh, use the equation we had before in action. So if we want to understand the rate of a specific reactant or a product, we're going to use this equation. Oops. Okay. The rate, let's work these. Okay. The rate is going to be equal, as we said before, to the change in something. We could put either A or B because, that's what we're using. But let's just say X just as a general, like we said before, the change in something over the change in time. Now, if we want something specific in this case, let's do B. Okay. So if we know that what delta is just the final minus the initial, right? So what are we gonna do? We're gonna do the final B minus the initial B. And it doesn't have just when we mean final and initial, it doesn't really mean that it has to be the 30 and the 0. We could pick either any of the two intervals we want. So we could do 30 and 10, we could do 30 and 20, we could do 30 and 0, we could do 20 and 10, we could do 20 and 0. It doesn't matter. As long as it comes a higher number to a lower number, because as we know, the reaction happens as time goes forward. So if we're getting our delta t, the delta t can't be a negative number. So if you end up having a negative number for your delta t, then you did something wrong. So a common mistake someone would do is, they have, their top number x minus y or whatever. And let's say in this reaction, I picked a time of 20 and I subtracted it by 30. And this number would end up being our delta time, right? And we'd end up having a negative 10 for this value. And that is wrong because we can't have a negative value for time because time is a positive number. Like it only goes forward. But anyway, I scribbled a lot, so let's lock in and we gonna uh find a rate for our thing. As we mentioned before, reactants have a negative rate and products have a positive rate. So that's also something we can look out for. So let's do the reactant. right? So let's pick two different things. But first of all, let's show you what the general thing looks like. So boom, we have, so the equation is moles of whatever you pick. So let's just pick A at a specific time. Let's say T2 minus the moles of A at another time. Let's say T1. And then we have the time T2 minus T1. You could also have it as just T final minus T initial. But as I said before, it doesn't have to be final and initial. It could just be a time and another time. So let's just plug in the numbers. So let's write this out again. We could pick anything. We'll just pick 30 and 20. So we have moles at time 2. So it will be 30. So we have here at time 30, we have 0 moles, right? And let's pick 20. And at time at 20, we see that we have 0.25 moles. Okay. And just take notice at this. You see that we're doing 0 minus 0.25, and we know that this is a negative number, which means we're doing it right because the rate of reactance is always negative. So if we're doing, in this case, if we're working on B and we saw that our top number is negative, then we did something wrong. And our time difference is 30 for T2 and 20 for T1. Now we just solve this. This would be what? Negative 0.25 over 10, right? So our rate would be equal to negative 0.25 moles per second. Oh, 0.025. Let's cut and try that again, please. Oh my God. Embarrassing. So embarrassing. 0.025 moles per second. All right, that was easy, right? So easy. Okay, so let's do it again, but with our reactant, or not reactant, our product. So, like we said before, what are we doing right now? Okay, boom. Moles of B at time 2 minus moles of B at time 1 over time 2 minus time 1. So let's pick some numbers. Let's do let's do 30 and 20 again because I want to show y'all something. So here for B at 30 seconds, we have 1 mole. And at 20 seconds, we have 0.75. Peep how it's a positive number, which means we're doing something right. T2 minus T1, again, 30 minus 20. And this is equal to 0.25 over 10 seconds. And this is going to be equal to 0.025 moles per second. Now look, remember our last answer? For the rate for A at that point was negative 0.025, yet our rate for B is 0.025 moles per second. So this means that our negative rate for A is the same as our positive rate for B, which makes sense because it's the same thing. We lose A and we gain B. So yeah, that's right. Now we're gonna step up the difficulty a little bit because before we just had A becoming B, right? And this is directly proportional, right? Same number of A, same number of B. Like if I told you to find a number for A, it's just gonna be the negative value for B at that same time, right? So let's try something else. Let's try 2A turns into 3 B. So 2 moles of A turn into 3 moles of B. Now, the general equation I'm going to give you is going to be this. As we remember before, negative delta A or negative delta of the reactant over the change of time is going to be equal to the positive change of B, which is the product in the change of time, right? Because remember, negative 0.025 was equal to the positive. But that's only when we have the same stoichiometric value for A and B, because it was just 1A turning into 1B. So what happens if we have 2A turn into 3B? While the reaction is just, it's always going, the rate is actually going to be different comparatively. So in this scenario, we have it like this. It would be -1, it would be a fraction. So -1 over whatever the stoichiometric value is, or the coefficient. So in this scenario, it's going to be negative half A, delta A, sorry, over time is going to be equal to the same thing like before, 1 over this value, which is the change in B over time. And why does this make sense? Because what do these fractions mean? So just to better visualize it, let's just have this 2A becomes B. So here we see that we have two A's becoming a B. So it would be this equals delta B over delta time. So basically, A is becoming B, but we have more A becoming the same amount of B. So it means that we're pretty much to like A is working harder because A is just not turning into A is just not turning to B. Two A's are becoming into B, which means that half of A is becoming B, which might be a little confusing to some people. But imagine I'm this guy, right? And I got a lot of money, right? And then, let's say that's me. And then there's you, right? And you got some money. You could say that half of this guy's money is equal to one of your money. You understand? So if I had three money, then 1/3 of his money would be equal to one of yours. So that's the relationship of it. So in this case, with two and three, half of A is going to be equal to a third of B, right? So that's kind of the relationship we have to understand. The higher the coefficient, it kind of means that the chemicals is transferring more to become the other. So yeah. Now we're gonna try and understand how we could solve for this numerically, which means we have to use a little bit of algebra. So our question is to find the rate of appearance of B when the rate of disappearance of A is 0.3 moles per second. So just like we did before, we're just gonna set up our appearance expression. So remember, products are negative, 1 over the coefficient of A, and yeah, delta A over delta T is going to be equal, this is positive, 1 over a coefficient for the change of B over the change of time. Now, remember here, we already have our rate for A, which is 0.3 moles per second. So we could just write it like this. Negative half of 0.3 moles per second is equal to 1/3, and we know that this just means the rate, so I kind of just like it better when it's like this, because at the end of the day, we're solving for the rate of b. Now, all we pretty much have to do is just solve for it. So we could just multiply these together. Negative half of 0.3, what is that? It's like what, negative 0.15 is equal to 1/3 for the rate of b. And to get b by itself, we could just multiply this by 3 and multiply this by 3. And we have negative 0.45 is equal to the rate of b. And the signs really don't matter because we know that b in this case is a product. So in this case is a positive number. So 0.45 moles per second is equal to the rate of b. And this makes sense because we see here that um it's just more because 3 is more than 2. And if you end up seeing something like this where like the reactant is smaller and this number you got for B ends up being smaller even though the coefficient is higher, then you messed up somewhere. So right now we went over like the rate of disappearance and appearance, but now we're going to be going over rate laws. And rate laws is essentially the relationship between what is the amount, the change in concentration versus the rate. So the general expression that we'll be using is going to be rate is equal to the constant K times something. Let's say A, B. This could really be anything. We're just going to use this as an example, or D. Right? And on top of this, we're going to have an exponent. And this is going to be the rate order. So this could be a 0, 1, 2, 3, 4, 5, 6, whatever. And this is the main number that's going to associate the relationship between the amount. This is going to be the amount, and this is going to be how it changes. So we're not going to use K just so we could understand the relationship between the like A and the exponent. So a way I kind of like to explain it is to write the equation like this. So this equation, how we have, forget about K right now. Rate is equal, let's just say A in this scenario, forget everything else, times whatever is this thing, right? Let's just use M to represent either 0, 1, 2, or 3. It's basically how much, so the rate is going to be how much the rate changes. So how much the rate changes is going to be equal to how much uh, A changes or B changes or C changes. A changes and it's going to be to the power of the rate order. So let's do an example with the 0 order. So let's say so how much A changes? So let's say in a first trial and a second trial, we go from A, we have 1A, and in the second trial, we have twice as much A, right? So how much has A changed here? Well, A changed by a factor of 2, right? It doubled. So A changed by 2. And let's say it's a first order reaction. Well, how much has the rate changed? The rate has changed by a factor of 2 to the first, which means the rate changed 2 by a factor of 2. So as A doubled, the rate doubled as well. So that means there's a direct relationship. Let's say at trial 3, A is equal to 3, right? Well, A is equal to 3 times by it being a first order. That means the rate tripled. As the concentration of A triples, the rate is going to triple. As if it goes up by 5, the rate is going to go up by 5. And that's basically how it works. Let's see what happens if it's a second order reaction. So let's do this. At trial 1, let's say B, we have one amount of B. At trial 2, B ends up doubling. So in a second order reaction, so we see that B ended up doubling. It's a second order reaction. If I ask you right now, how much has the rate changed? Well, it'd be equal to 2 squared, which is equal to 4. So the rate, how much the rate changes, rate went up by 4 times. Let's try a different one. What happens if the amount of B went up to 3? Well, it'd be 3 squared, which means the rate went up by 9. Now let's do this. I'll give you a question. In a second order reaction, if the concentration went up by 5, how much did the rate go up by? Did the rate increase? So we just plug in. How much has it changed? Changed by 5 times. What's the order of the reaction? 2. How much has the rate changed? 5 squared, 25 times. And that's just basically with everything. What about a zero order reaction? We know that anything times 0 is equal to 1. Therefore, if let's say it changed by a factor of 2 to the 0, the rate will change by a factor of 1, aka it won't change, meaning a zero order reaction is independent from the increase in concentration. For first order reaction, if it increases by factor 2, it'll also change by factor 2. And the first order reaction, if it goes up by factor 10, it's the same thing. And second order, if it goes up by 2, rate will go up times 4. Third order reaction, if it goes up by 2, then it'll go times 2 to the 3, which is what, 16? So that's basically how uh the rate order, the relationship between concentration and the whatever, how much the rate changes. So using what we just learned, let's try to find the rate law for each. So uh let's look at this. So we see for B ended up doubling, right? And when B doubled, what happened to the rate? Well, the rate went up by 4. So what does that mean? Well, you could kind of just infer that it's a second order reaction because, you know, you should just like know in your head if it went up by 2 and the rate went up by 4, then it's a second rate reaction. But what we could actually do is just we could try and do it mathematically because there's going to be situations where the numbers are kind of harder. Like this could end up being scientific notation. It could be like 1.6 times 10 to the negative 9, like some crazy number like that. So it's not going to be as easy as just like looking at it and realizing, oh, it went up by 4 or it went up by 2. But we could see that it's a second order reaction. But how do we do it mathematically to where no matter what number there is, we're always able to figure it out, even when it's not as easy? What we could do is we could divide the things that we're looking at, right? Why am I doing all this? So let's isolate this scenario, right? We could do like before, we could find the concentrations that we're working on. So here, it was at 2, then it was at 1. And this is gonna be, and we're gonna set it equal to the change, eh, the rate. So it's gonna be like 2 for 0.5, and it's gonna be like, and then it's gonna be like to the x. So it's gonna be like 2 to the x is gonna be equal to 4. We're gonna see like it's like literally like 2 to the x to the 4, and you literally oh wait, crap. It's like 2 to the x equals 4. So then you just see that this like gotta be 2. But what if like this is like 1,069,069 and like this is x and this is equal to like 1.10 times 10 to the negative 10? Like it's gonna be mad difficult. So what you actually are supposed to do is just find the log. So using using the log, you'd realize you just do log. It'd just be log 4 over log 2 is equal to x. It's gonna be equal to 2. So yeah, the second order reaction. Good job, guys. We here to